will be some theoretical introduction, and then I'll apply this analytical consideration in order to calculate the possible effects in dilepton production at the LHC, in order to get reach limits of the LHC in searching for effects for extra dimensions. The problem of the topic is the following. After reproduction, I'll consider one extra dimension with the non-zero curvature. This curvature will be taken to be very small, and then I'll consider the process with the exchange of this channel basic contributions which arise in all such kind of theory, and the main goal from the semantical point of view will be to consider direct production of the LHC. Okay. This is just a few names of people who contribute to the extra dimensional physics. Because to consider 5 vector theory in order to get a scalar in physics described by the one unit or two. Then line and forth, and also Einstein also previously mentioned the relation with extra dimension. Okay. Why people consider the partial but not time-like dimensions? You can easily see that if you suppose that the extra dimension has time-like metric, then you will obtain tachyon from the point of view of 4-dimensional observer. That is why I consider only partial extra dimension. In our case, it will be only 1 dimension. As you know, it is strings theory which lead to the existence of possible existence of extra dimensions. For instance, superstring needs 10 dimensions, 6 of which must be quantified, not to be contradicted with our low energy physics. And moreover, the string theory predict the existence of space in the dimension which are called grades, on which the ends of open strings move. So if you start from, say, string action and integrating extra dimensions, there are 2 parts from the gravity part and the gray part, and if you obtain effective action, you finally get the so-called hierarchy relation, which explains the very large values of quantum scale in 4-dimensional scale in terms of very large volume of this extra dimension. This is a so-called large volume scheme of ADD model. So let us consider the Randall-Sundrum scenario, but I will vector, you can obtain easily large value of mass square. If you take this product of D over the rule. So it is assumed that there are two branes in which on one of which the so-called PD brane, all the standard model fields agree, and the gravity is in all dimensions, and it is very strong on this on the other brane. And you can obtain the value of this metric if you start from 5-dimensional action. There are two parts, one which is gravity part, usual one, but in 5 dimensions. Y is the 5 coordinate corresponding to this x dimension. And there are also two parts corresponding to matter on branes, and there are also cosmological 5-dimensional cosmologicals, and also two brane cosmological constants. And this method was solved with a well-known paper by Randall-Sundrum, and the answer is the following. See that it's dependence on and the curvature is given by this effectively this scalar curvature is proportional to the scale of this. There are some formula which enable to get the above solution. Let me show you just that if you consider this scalar curvature, you will see that only the value that is in between the branes, you have this well-known proportionality between which tensor and metric tensor, and the curvature is indeed given by this parameter kappa, and the radius of the curvature is the inverse value of this. If this kappa is indeed the curvature of the 5-dimensional space. So, as you know that in the Randall-Sundrum model, the Halos-Plane gravitons arise, and in addition, scalar field also present in the theory, and the graviton masses appear to be proportional to this parameter kappa, contrary to the Randall-Sundrum model, in which the masses can be very large. For instance, you can get a very small value for this kappa around, say, 100 GeV or 1 GeV in order to obtain not very large values of these masses, contrary to the Randall-Sundrum model, in which these masses are order of 1 TeV or 10. As for Newton's potential, the possible corrections to Newton law is very, very small. It is negative. Moreover, there is no statistical bounds on this model, even for very small value of the curvature. As for interaction of Grandjean, it is very similar to the Randall-Sundrum model with the large curvature option, but in the Randall-Sundrum model, both the curvature and the Planck scale, this is the scale or Planck scale in 5 dimensions, they should be a model of Planck scale, but in this scheme you can choose, for instance, these scales around 1 TeV. In such a case, you obtain TeV physics, but maybe it's more interesting to consider the so-called small curvature option, in which 5-dimensional Planck scale is order TeV. Order 1 TeV, while this curvature can be much smaller than 1 TeV. That's why I call this Randall-Sundrum-like scenario as a Randall-Sundrum small curvature model. And in such a case, you will obtain the almost spectrum, which is very similar to the case of extra similar or equivalent to the case with the one extra dimension with a very small width flat metric. It can be shown that in order to get this flat metric limit, you should choose this parameter capital very, very small. So even at almost all the reasonable values of kappa, this scenario is not equivalent to the extra dimension with one extra dimension, which flat metric. So let us consider taking into account the Randall process, the contribution from these massive gravitons with the properties described above, this process, for instance, to dilepton production, again, jets. So these approaches are the following. There are co-combinations approaches and also long-term fusion. And unfortunately, the matrix element can be calculated analytically. For instance, you see the matrix element is the product of two parts. One is the convolution of tensor momentum, energy momentum tensor of initial final particles, and another part S is universal for all exchanges and can be calculated, as you will see, analytically without any approximation. Usually people use so-called zero-width approximation, that is, they ignore these widths of the massive gravitons, and I'll show you below the picture which will demonstrate that this ignorance is not justified. Of course, in such a case, the calculation will be simple, but the count of the widths of the gravitons is very important. And so you can calculate analytically this expression for this value, for this quantity S, using the well-known formula for this formula for basic functions. Remember that the masses of gravitons are proportional to the zeros of the basic function x, y. We use this formula and update analytical expression for the amplitude. Let me miss some slides and not exceed my time limit. And it can be shown that from the theoretical point of view, the spectrum can be regarded as continuous only if the energy is large enough as compared with its high-dimensional gradient, high-dimensional landscape. And it's interesting that the same takes place also for Dnepropetrovsk. Resonances in such a case are very narrow. Nevertheless, the distances between resonances are much larger than the widths of these gravitons, also in AD. So let's consider dilepton production in both the dimension. So this is Randall process. The dilepton could be muons or leptons, and this is well-known formula for the PT distribution. The scale of the dx taking the mass of the pair, and by using this formula you can calculate the contribution, but before I show you some energy and dependencies of standard model distribution and gravity distribution. You see that standard model distribution, PT distribution, decreases some power of energy at fixed values of this quantity, and gravity almost show you some calculation results of some calculations for dynamic production and dilepton production. I will use the relativity cutting both as CMS, efficiency, and in order to take into account possible next to leading contribution to the standard model requirement. I will use this effect for standard model cross section to be 1.5, so 1.04. This picture shows us the dependence of this T-distribution with the function of dilepton transverse momentum for 7TB for different values of current dimensional class. And the dotted dashed line is the cross-section T-distribution for the standard model for the distribution. This is the same but for 14TB. And different values of this scale. And this is the ratio of the gravity-induced cross-section to the standard model cross-section. You see that for non-very large values of gravity scale, the ratio would be very large as compared with the standard model cross-section. Especially for large values of because the standard model increases more rapidly for large technique. So this region is more effective for switching some radiation from standard model distribution. In order to show you that the count of the bits of the gravitons is very important, I'll show you this picture. You will see, for instance, that these solid curves correspond to the formula presented above, and these dashed curves correspond to the zero bits case, but multiplied by this 1,000. So this contribution are very negligible with respect to the exact result, even for very large values. That's why the count of the dilepton bits is very important for real calculations. So as for the dilepton production, the only difference is to take into account the slightly modified relativity cuts. I show you the cuts are seen as the atlases. Cuts are always the same. There is some difference. And let me show you the sections for 8 TB as well as for 6 TB. And this slide shows you the statistical significance for the process for the dilepton production as a function of the high-dimensional gravity scale and TP. So I use events for I use a number of events with which correspond to the large TP transverse momentum of the dileptons, that is, for instance, larger than 200 GeV or larger than 300 or 400 GeV. And the claim statistical significance equal to 5%, shows estimate the which mean this is the same but for 14 TB and the University of came directly down this gravity system. So in underline the account of the graviton bits is very important. It was not done in other papers. It appeared to be very important for numerical calculations. And the research limit can be extracted from previous figures are the following for the combined energies 7 plus 30 the possible search limit on this bounds on this one-dimensional gravity scale is 6.35 dB, and for this energy and 30 universal per barn, I expect that the search limit will be even larger than 8.95 dB. Let me note that these values are larger, significantly larger than the search limits we could expected in the standard model scenario with a large curvature. So just after conclusion, one more conclusion. You can ask how to discriminate between this gravity text from other binocular standard model procedures. For instance, let us assume we'll see some deviation from the standard model. I see two points which will enable to do such a discrimination. The first is the following. It's known that the branching of the gravitons into two photons is twice branching for dilepton reduction. It means that one can relate the contribution from the diphoton and the Randall process, taking into account that the interaction of these gravitons with the initial particles is universal. And another part is another point is that graviton is a spinning particle. I expected that Alexander will talk about his papers on spin. That's why I mentioned this here. And it is known that and the distribution in standard model and vector particle exchanges are proportional to the 1 plus certain power of cosine theta. But if you have spin 2 particles, additional term proportional to this term. This present process for combination dependency is the same, and for Young fusion dependencies is the same. These terms are not present for standard model contribution, and just show you this picture. This yellow line is the contribution from speed 1 particle as a function of. And as for spin 2 contribution, the angle becomes as difference. Okay. So I try to be not to exceed my limit, but say I have a lot of time, maybe answer questions. So these 2 points maybe will enable to discriminate these standard model specific contribution from extra dimension from other numerous contributions from other models beyond the standard model. Because I have time, maybe I will show you some a few words experimental point of view, there are systematic errors related to the luminosity as well as the measurements of dilepton displacement and also energy resolution. We try to estimate some possible uncertainties and so the first line is corresponding. If you consider change this scale from invariant mass dilepton divided by 2 to 2, invariant mass corresponding to deviation in the relative scale is approximately to also for some possible errors related with the luminosity of the PDF distribution. So the order of this deviation is about 15 relative to 11 is maybe maybe some general conclusion concerning extra dimension in general. Extra dimensions, not only this scheme, of course, can explain hierarchy relation between the electromagnetic scale. Also, for mass hierarchy, and many other things, because the weak symmetry without things, we know that it's this, there are supersymmetry with ramifications, so and you know that I also demonstrate that the explanation lead to a wide range of new phenomena, especially new particles which can be detected at colliders, and you can extract these effects and know more about our space-time. Okay, thank you.
Any questions?
What are the current limits for the Randall-Sundrum expressions
For this agreement, yes. Let me show that. Usually people check several possibilities. First, so-called the extra dimensional displacement, the bounce of the flow, you see. Well, it depends, of course, on the number of extra dimensions.
well, they seem to be higher than those regions that you showed us on those plots, where from some 400 GeV to 1.1 GeV for the searches of those separations. So, are there some maybe missing?
No, I think that these bounds are almost can be regarded as a very established strong.
But earlier you showed us some plots where there were the standard model plot and standard model plus calcified excitation, and they were in the range from 400 GeV to 1.1
Yes.
GeV. And what do we have to look there? They are close. They are ruled out.
First of all, I have to say that these limits are paid for not for this scheme, but for another extra dimension model with flattening. So its limit doesn't relate with this. As for Randall-Sundrum scenario, there are limits. For instance, this limit, which is given for the case when you have a very large curvature and the spectrum consists of very heavy resonances. So again, this case is not the same. The people is now prefer to look for these heavy resonances. Maybe it's more easy. So and you see that this limit depends on this.
Okay, and I have another question. What
slide you showed the comparison of your approach with, let's say, gravitational force at small distances. I mean Newtonian force. And there are current experiments which measure this force at distances, I think around 1 centimeter or so. Do you have any constraints on your parameters from this?
No? Unfortunately, as I have shown, the relative corrections in this scheme to the usual Newton norm is 10 to the minus 15. So at least at this distance is up to tens of millimeters. So I hope that in the nearest future it will be impossible to put some bounds from gravity experiments. So the only hope is to look for this gravity effect in the collider experiments.
Any question?
I'm confused a bit of your distributions, cross sections versus transverse momenta. It seems it was the first figure.
This is correct.
Не зависает, там есть пауза, наверное, на этом. Нет? Опять зависит.
Прожектор доплатит, баланс
should be, it seems, this model, standard model plus this why this intersection of this process occur.
Did you ask for interference? Great interference? Did you?
This standard model, okay, but then when I switch on to the extra dimensions, it should be some sort of deviation from this standard model behavior.
No, this is just the standard model contribution. This is pure gravity contribution. Pure. As for interference, too, they are very, very, very small lengths, but due to some cancellations. So it's a pure.
Any question? I have one remark. The particles you have discussed must be excluded as a candidate on the weakly interactive massive particles which enter to the whole dark matter. Because the latest experiments shown that the mass of this particle must be in the region of 10 GeV only. 10 GeV.
I didn't mention that.
Your particle is very heavy.
Yes, but you can choose this kappa to be equal to 10, maybe then the
10.
lightest one will be 30, 40 millimeters. So it could be, but I didn't insist on the fact that these particles should be
Very
candidate for black matter. It wasn't.
Yes, what is the low bound on the mass this particle you have used? New limit, or low limit on the mass.
The goal of my paper, my talk was to get some limits on this. The limits are dependent on this kappa. Kappa can be chosen not very arbitrary, but the only fact that this kappa should be much smaller than this, and not very small.
So you could obtain the mass in the GD region.
In
For this
GB or even
Okay.
tens, 100 dB.
This depends very much on the number of extra dimensions. And only 3 to 6 extra dimensions are allowed. All the others excluded.
Okay.
For the reasons what you mentioned.
I can comment.
Let's thanks to speaker again.